Have you ever been waiting at a junction and felt a massive lorry pull up alongside you, heard that enormous hiss of escaping air, and wondered for a second whether something had gone wrong? The sound is hard to ignore. It's loud, sharp, and slightly unsettling, like a pressure valve releasing somewhere inside a machine that's working harder than you can see. But that hiss isn't a warning. It's the sound of one of the most elegantly designed safety systems in the history of road transport doing exactly what it was built to do. Your car stops using hydraulic brakes. Press the pedal, fluid moves, pads clamp, friction slows the wheels. It works reliably for a vehicle weighing 1.5 tons. Now imagine that same principle scaled up to a fully laden articulated lorry, weighing 40 tons or more. The numbers don't just get bigger. The physics change entirely. Every year, heavy vehicles travel billions of miles on roads shared with ordinary cars, cyclists, and pedestrians. A braking failure on a 40-ton truck traveling at motorway speed is not a minor incident. The consequences are catastrophic and irreversible. The braking system carrying that responsibility cannot simply be a larger version of what works in a car. It has to be built around a completely different principle, one where failure itself triggers safety rather than disaster. But here's the surprising truth. The key difference between a truck's air brakes and the hydraulic system in your car isn't power. It's philosophy. A hydraulic brake releases when the system fails. An air brake applies when the system fails. That single inversion of logic is the reason that every heavy vehicle on the road today uses compressed air to stop, and it traces back to a problem that engineers were grappling with long before the motorway existed. To understand why, we have to go back to the early days of heavy freight vehicles, when the braking systems available were essentially borrowed from horse-drawn carriages and scaled up by instinct rather than engineering. Mechanical brakes using cables and levers worked adequately on lighter vehicles traveling at low speeds. But as steam-powered and then diesel-powered lorries grew heavier and faster through the early 20th century, the limitations became impossible to ignore. Cables stretched, drums overheated on long descents, and crucially, any failure in the mechanical linkage meant a complete loss of braking at the worst possible moment. The person most exposed to that risk was always the driver. Engineers understood that what heavy vehicles needed was not a more powerful version of the existing system, but a fundamentally different one, where the default state of the brakes was on, and where the driver's input was not applying the brakes but holding them off. There was a second problem that mechanical and hydraulic systems shared, one that became brutally apparent the moment heavy lorries began crossing mountainous terrain. Braking generates heat. On a long descent, a driver braking repeatedly to control speed transfers enormous amounts of energy into the brake drums. Hydraulic fluid heats up. As it heats, it can vaporize inside the lines, and vapor compresses where fluid does not. The pedal goes soft, then softer. Then, on a steep enough hill with a heavy enough load, it goes to the floor and does nothing. This is called brake fade. And for early freight operators navigating alpine passes or the mountain roads of the American West, it was not a theoretical risk. It was a recurring catastrophe. Air does not vaporize under braking heat the way hydraulic fluid does. The compressed air system sidesteps brake fade almost entirely, which made it not just safer in the event of a mechanical failure, but reliably more effective on the long descents where hydraulic systems were most likely to let drivers down. Compressed air was the answer, and the logic is straightforward once you see it. Think of it like a heavy spring being held back by your hand. The spring wants to close. Your hand is the only thing stopping it. The moment you let go, the spring snaps shut. Air brakes work on exactly this principle, Powerful springs inside each brake chamber are always trying to push the brake shoes against the drum. Compressed air is what holds them back. The driver releases pressure on the pedal, air flows in, the springs are held in place, and the wheels turn freely. The moment air pressure drops for any reason, whether the driver steps on the pedal deliberately or a line splits or the compressor fails, the springs are released and the brakes engage automatically. The truck stops. The failure mode and the safety mode are the same thing. So, if the brakes automatically apply whenever pressure drops, what stops them locking on constantly as air leaks slowly from the system? The answer, as is often the case in history, comes down to layers of redundancy built in at every point. The air compressor, driven by the engine, continuously replenishes the system, feeding compressed air into a set of storage tanks large enough to allow multiple full brake applications even if the compressor fails entirely. A governor valve monitors pressure constantly, signaling the compressor to stop when the tanks are full and restart when levels fall below a safe threshold. A dual circuit design splits the system into two completely independent halves, one serving the front axle and one the rear, so that a failure in any single line can never take out more than half the braking capacity at once. And running through all of it is an air dryer, stripping moisture from every cubic meter of air that enters the system. Because water condensing in the brake lines and freezing in cold weather was one of the earliest and most dangerous failure modes engineers discovered. Every component in the system is designed not merely to function, but to fail gracefully, handing off to a backup before the driver has any reason to notice. The same spring mechanism that engages automatically in an emergency also serves as the vehicle's parking brake. When a driver pulls the yellow diamond-shaped valve in the cab, it exhausts the air holding the rear spring brakes, locking the truck securely in place without any mechanical ratchet or cable. A fully loaded lorry parked on a hill holds itself there not through effort, but through the permanent tension of those springs waiting to be released. This is why operating a vehicle with an air brake system requires a specific license endorsement in most countries. The system behaves in ways that are not intuitive to drivers trained only on hydraulic brakes, and understanding the difference between a soft pedal and a correctly functioning air system is not something you can learn by instinct alone. This is the engineering philosophy that makes air brakes the universal standard for heavy vehicles, and it is the reason that a system developed in the early 20th century remains, in its essential principles, unchanged in the vehicles sharing the road with you today. So the next time a lorry pulls alongside you at a junction and you hear that sharp hiss of released air, you'll know what you're hearing. It's not a fault. It's a system exhaling, resetting, holding itself in the ready position for the next time it's needed. Hydraulic brakes are held on by pressure. Air brakes are held off by it. The difference is invisible until something goes wrong. And that is precisely the point. The best safety system is the one that works hardest in the moment it's needed least.